Hello. Today we will be doing some problems on dimensionless numbers and the topic of scaling and dimensional analysis. So here's a problem. It tells you that there is a smooth steel ball immersed in a flow that goes at 1.5 meters per second, and it's a straightforward application that they ask you to estimate the drag in newtons on that sphere due to the stream. So here's the problem. You have a sphere and it's in a stream of ethanol, and naturally there would be a drag force due to the resistance of the so it's the flow resistance to the presence of the sphere, and it's the reciprocal reaction from the sphere on the flow. So how do we do this? They tell you to go to figure 5.3, but what that figure is about is it's a plot of the drag coefficient as a function of Reynolds number. This actually should be the drag coefficient rather than the drag force. So the drag coefficient, it's not FD, it's CD. The drag coefficient, so let's just fix that. The drag coefficient depends on the Reynolds number, so it's CD over here. With Reynolds number being, as we have defined it before, so for you to find the drag coefficient from which we can get the drag force, you really need to know what the Reynolds number is. So we can compute the Reynolds number if we know what the flow properties are, density, viscosity. So we have those for ethanol, the density and viscosity. And we know that the flow velocity is 1.5 meters per second. And we also know the diameter of the sphere, this diameter. So you plug them in, you get a Reynolds number of 25,000. And then you go to the figure, which shows the drag coefficient plus the drag coefficient versus Reynolds number. And we go and plug in the 25,000. It's somewhere here. So you see there's it's a log scale, log linear scale. So that's 10,000, that's 100,000, and 25,000, some almost halfway in between. And you have two curves, one for a cylinder and one for a sphere. So for the sphere is the problem that we're looking at. You get a drag coefficient a little bit less than half. So you get a CD of about 0.4. And now the definition of CD is related to the drag coefficient. So, that drag coefficient is often based on a certain length scale or a property of the length scale. Here we're talking about it's the area, and that area is the frontal area of the sphere. So or the projected area. So we plug in numbers. We have the CD of 0.4. We have the density and the flow velocity and the frontal area, the pi r squared. So that's the frontal area we're talking about. So you get a force of a small force of 0.17 newtons. And they ask you if you double the stream velocity, so if you go from 1.5 to 3 meters per second, what do you expect? Just because the drag force goes with u squared, so you see here the 1.5 is squared. If you go to 3 squared, this number is going to quadruple. Great. So let's do one more problem here. They tell you, if you look at the parachute in this figure, it's designed for Martian missions, but it's tested first on Earth, and when it was tested in a wind tunnel, it gave a drag coefficient of 1.1. And here they explicitly explain to you that the drag coefficient definition, the area in the definition of the drag coefficient is the projected area, which is this area that we are talking about. So that has to be explicitly defined in whatever problem you're talking about. But now we get this. So we've seen it for a sphere, and now we see it for a parachute. So on Earth, testing shows that the parachute descent rate at an altitude of 1,000 meters in the atmosphere was 30 kilometers per hour. So the question is, what is the weight of the object attached to it? So here's what we have. We're given a parachute. There's a load attached to it. So here's the parachute. There is a load. There you go. It's plotted over here. You have a parachute, a load attached to it. And we know that when you do this test on Earth, you get a velocity of 30 kilometers per hour. The altitude at 1,000 meters, the atmosphere has an air density of 1.11. So the question is, what is the weight of this load? So there are some keywords. One keyword is it's a steady descent. So there's the phase when this first drops from an airplane or gets dropped. Initially it has zero velocity, but after it has a zero velocity, it starts accelerating. But then, so let's see what happens when it starts accelerating. In the absence of atmosphere, it's going to keep accelerating. Every second it's going to gain 9.8 meters per second of speed. That's the G. But since we don't have, since friction exists, and it's the air friction, at some point, and the air friction, as we have seen, the drag, the F drag goes with the velocity squared, as we have seen from the previous example, scales with u squared. We expect at some point, if u is too large, the drag coefficient is going to be much larger than the weight, that the weight is going to stop in its track. But that doesn't really happen. There would be a balance at a certain, so there's an initial phase of acceleration. It takes maybe 1 or 2 seconds or 3 seconds. And then at that point, the drag force, because you get to a speed where the drag force becomes equal to the weight. So then you get to phase 2, where you have a steady travel of the parachute and the weight until it hits the earth, surface of the earth. So we expect that we have a balance between the frictional air forces and the weight. Here we're given, so we have, since we're in steady descent, the acceleration is 0, so the summation of external, so there we don't have acceleration. So the external forces in the vertical direction and the travel direction, the summation of the acceleration is 0, so the summation of external forces on the system are 0. So if I take the object, it has the weight pulling it down, and it has the rope pulling it up, which is the reaction force. The rope is attached to the parachute, and the parachute sees the drag force. So we'll just, it's tension here, but we'll put F drag following that argument. So my drag force will be equal to the weight, which the weight of the body. And then, as we have seen in the previous slide, the drag force scales with the velocity square, the projected area, and the drag coefficient. So there's a relationship between the drag force and the drag coefficient. And in this case, they make our life easy, and they tell us what the drag coefficient is. In the previous slide, we had to go find that drag coefficient based on the problem parameters, because we had the figure that belongs to a sphere. We don't have a figure for a parachute, but it's given to us. So you plug in numbers. We're after the weight of the payload. We have the descent velocity. We have the frontal area, which is the pi r squared. and we have the drag coefficient of 1.1. So you plug those numbers in. The descent speed is 30 kilometers per hour, which is 8.3 meters per second. And this is CD. So that's half rho squared. So it's only one. It's repeated, and that's equal to the weight. So you can get the weight to be 0.98 tons, or 980 kilograms. So the next problem, we're going to revisit the initial question we started looking at in this chapter, which was, imagine I have this car and I'm still designing it, and I would like to get an estimate of how much drag force it's going to generate. So we said we can build a smaller model that looks exactly as the car. So you can see it's a scale. So here it's a bad example just because these have to look exactly the same. But imagine that they're exactly the same shape, but of different scales. So that's the point here, is that we have different scales. We can now take this, because it's cheaper to make, we can make it out of wood, we stick it in the wind tunnel, and then we get, let's say, drag force of 20 newtons. So we found the drag force on the little car, the toy car that we have, but that doesn't answer our question, what is the drag force on the actual car? So that's what we want to do next. So that's what we call scaling up the test result from the small scale to a large scale. In certain situations, it's easy, and these are particularly very, very small when we're dealing with small objects, like if you want to understand the flight of a bee, or even a smaller insect, you might want, because it's harder to manage a bee or manage a model of a bee and build a model of a bee, you might want to build a scaled up model and then go down to the real life. So you can, there are tests in the literature that you can see them, you can be scaling up or scaling down. So you can go either way. But going either way, whether from model to prototype or the other way, we need to know how to do that. So there are a couple of conditions for us to be able to extrapolate the results from the small scale test to the actual prototype. So let's define two terms. One is the model and one is the prototype. The prototype is the actual object, is the actual car that we have in the previous figure, and the model is typically the toy model that you build. So for you to be able to scale up and scale down your results, you really need to have the geometry be the same. You don't want to model this wing with a sphere. So you really want to replicate every aspect, as many aspects of the design as possible, and if it's the same, then that's even better. So here are two geometrically similar models, just because all the shapes, all the lengths have a certain ratio, all the angles are the same, just because the angles are ratios of lengths. And here you see we have four different models of three models of a prototype, and we need to have geometric similarity as an initial condition for us to be, or as an existing condition for us to be able to extrapolate our results. And here you see an example that, because we're after the fluid dynamics forces, and you'll see here that the flow pattern will look more and more the same if you have the same shape. So it makes sense. That's more of an intuitive argument. Then the next condition, so if you don't have geometric similarity, scaling up and scaling down your results will become, will deviate more and more from the actual truth of the sought after result. The second condition for us to be able to extrapolate is to have dynamic similarity between the model and the prototype. And what that means, so let me just take you back on what we mean by dynamic similarity. Dynamic similarity is about the force ratios. So now that we have the length ratios and the geometric ratios to be the same, now we want the force ratios to be the same. And what does that mean? Let's look at something like the Reynolds number. Reynolds number, we derived it from the Navier-Stokes equation. And the Navier-Stokes equation is a force balance. So we ended up also showing that the Reynolds number was the ratio between the inertial forces in the flow relative to the viscous forces in the flow. So if I have to, if I want to get the drag coefficient, so before I go there, so it's the ratio of those forces in the flow. So I have to have, if I have two models, a big one and a small one, then I require that the ratios of inertia to viscosity in model 1 will be the same as the ratio of viscosity to inertia in model 2, which means I require an equality of Reynolds number. And we have seen in the example of the drag coefficient versus Reynolds number that the drag coefficient is a function of Reynolds number according to this plot. And what this plot tells you is that you have the low Reynolds number region, which we call the creeping flow or Stokes flow, Reynolds number less than 1. And then we have the high Reynolds number flow, which is above 100 to 1000. And that makes a big difference. So whether you're in regime A, in the Stokes flow regime, or in the high Reynolds number flow regime, or the inviscid sort of flow regime, where your drag coefficient is independent of Reynolds number, depends on Reynolds number. So that's why and that plot tells us that the drag coefficient is a function of Reynolds number. So if I want to predict what my model is going to give me, I need to guarantee that my model and prototype have the same Reynolds number. And then when they have the same Reynolds number, then the ratio of the drag forces between the model and prototype will also be the same. Since this is an internal to the model, but then to extrapolate, once I guarantee that the internal properties are the same, then I can, and I have geometric similarity, then I would expect that the forces will extrapolate because the drag coefficient will be the same. And this is a result of our Navier-Stokes equation, because this was derived from the normalization or the infusion of the scales into that equation. And we also, if you remember, we looked at the Reynolds number to be not only the ratio of inertial forces to viscous forces, we thought of it also as ratios of length scales, time scales, and velocity scales. So we now have a feel that that by using scales we can easily think of them as force ratios and or velocity ratios. And then once we have this this in mind, that to have dynamic similarity for us to be able to scale up and scale down, then we can, and we've thought here we gave the Reynolds number as an example, but if you look at the literature, there are so many types of problems. So Reynolds number, we're almost always going to see it. We're almost always, not every time, going to see a relationship like this. Like Strouhal number is a function of Reynolds number, or the drag coefficient is a function of Reynolds number. So there's always something that's function of Reynolds number. But there are other cases where Reynolds number may not be that important, like in compressible flows. So would be your clue that tells you, so this part of the table that you have seen before will tell you which number you really want to look at. So if you're looking at bubbles and droplets, you want to look at Weber number. But if you're looking at a ship, you're building a ship model that moves on the surface of the water, then you want to look at the Froude number, because the Froude number, your drag coefficient, lift coefficient, whatever forces you're looking at will be a function of Froude number. And there are regions, there would be plots like this that would have Froude number based on Froude number. So that's about it about scaling the test results from model to prototype. Is you want to have geometric similarity, and then you want to have dynamic similarity. And what it means to have dynamic similarity is to have equality of the appropriate dimensionless number, whether it being Mach number, Froude number, or whatever. And once that happens, then we can guarantee that the drag coefficient will be the same, just because Reynolds number is the same, or Mach number in that case would be the same. So let's look at an example now. Here you have, they tell you have a 1/10 scale model of a supersonic wing tested at 700 meters per second. So here's a supersonic wing. And it is being tested in a wind tunnel at sea level at 700 meters per second. So that's a supersonic wind tunnel. And when they do the test over in the wind tunnel, they find a force of, on this toy model, 1/10 of that. So if this was let's say 5 meters, the toy model would be only half a meter. It's 10 to 1. And they measured a pitching moment of 0.25 kilonewton. So a pitching moment is a moment around some rotational axis. So it's a moment. It's a moment due to the pressure distribution over the top and bottom of the wing. So here they tell you, don't worry about Reynolds number. Reynolds number effects are negligible. And they ask us now, if I want to look at this real test, I did my wind tunnel test, but now my airplane is moving not at sea level, but it's moving at 8-kilometer altitude. And here they give us a hint that the Mach number between the model and the prototype are the same. So they're sort of telling us you have dynamic similarity. Not only do you have geometric similarity from the first statement by saying a 1/10 scale model, but here they're giving us a hint that we have dynamic similarity because they are flying at the same Mach number. So the question is, what moment should I expect in flight if the moment I found in the wind tunnel was 0.25 kilonewton dot meter? So here's what we have. We have the length of the model is 1 unit, while it is 10 units in the prototype, so it's 10 to 1. So you see, I don't have I don't have whether it's meter or kilometer or centimeter. That doesn't matter because it's not given. We don't have an idea of what that is. We only know about the ratio. But then we know that the speed in the model, that is the toy model, is the supersonic wind tunnel has a 700 meter per second test speed, and that's the pitching moment that we found. And here are the flow properties in the lab, which are 20 degrees C, 1.2 kilogram meter cube density, and a speed of sound of 340. We don't know, so now I think we don't know what speed at which the prototype is going to fly, and definitely we don't know what pitching moment we are going to expect. So we sort of have two unknowns. And then we know what the properties are at 10 or 8 kilometer altitude. So we have 37 degrees C below zero, density of half kilogram per meter cube, and a speed of sound, it's slower than it is at sea level of 308 meters per second. But we have a statement that the Mach number is the same. So let's see what Mach number is. Mach number is the flow velocity divided by the speed of sound. Great, so this is our speed of sound. So if they're both equal, then let's equalize them. The Mach number of the model will be the Mach number of the prototype. So I have the speed of sound in both cases, and I have the flight speed in the wind tunnel test. Then I can get the speed at which this prototype is going to fly in the air, the actual system. But then let's go to our question. So now we found the speed to be 634. So that fills up our table. And then let's go focus on our question is, what is the pitching moment? And so what this problem is stating, it's stating that the pitching moment, for you to get the pitching moment to scale up, you have to have the Mach number the same. So we have Mach number the same, but how do we scale the pitching moment? The pitching moment has units of kilonewton per meter. But if I were to tell you what is the drag coefficient, instead of telling you, instead of being the pitching moment, I'll tell you the drag coefficient is the drag force on the test model is 0.25 kilonewton. We know in supersonic flow, or at least we can expect that the drag coefficient should be a function of Mach number for us to have dynamic similar. So the drag coefficient will be a function of Mach number. And if I have the same Mach number, I should expect that the drag coefficient in both cases to be the same. And we know what the definition of the drag coefficient is. And the drag coefficient is just it's a force coefficient. We have drag coefficient, we have lift coefficient, and whatever other force coefficient you would like to have. So it's a force. And now if I multiply that force by a distance L, and that's by a distance L, then that, and here L, then that would be a moment coefficient. So we sort of sheeted by knowing the force coefficient, we can expand it to give us a dimensionless moment coefficient, which is just the moment divided by half ρ square, and you'll see the extra little term, the L, just to get the units scaling. So here we can write that Cm, the moment coefficient, is a function of Mach number. And if I guarantee that my Mach number is the same, which it is, as stated in the problem, then I will get my moment coefficient to be the same. So yes, my moment coefficient for the model will be the same as the prototype, just because of this statement. And then we have sort of defined, we didn't go to the table, we made our own moment coefficient, we defined it. And so the moment, here I have the moment, the density, velocity, and length scale for the model is equal to for the prototype, so that's prototype. And then plug numbers, I have 0.25 kilonewtons for the M. The density, velocity, and length are in the wind tunnel test, 1.2, 700 meters per second. And the length, we don't have units, but it's 1, just because here it'll be length scale ratio. So I don't care what the actual units are. And for the prototype, I don't know what the moment is, but I have the density at 8 kilometer to be half kilogram per meter cube, and I found from Mach number that I'll be flying at 634, and the length is 10 units of the prototype, while the length of the model is 1 unit. So it'll be 10 cubed. So the only unknown here is the moment, the pitching moment on the prototype. So we find a pitching moment of 88 kilonewton meter. So you see, it's not a scale of 10. If you started this problem by saying, well, if it's a 10-to-1 model, then I have 0.25 kilonewton meter on my toy model, I should expect 2.5 kilonewton meter on the actual prototype. That would be a big issue, because you see it doesn't scale with it doesn't scale linearly with the geometry. It has all those other factors too: the density effect, the velocity effect, as well as the length scale effect. The length scale effect is the more important one because it's cubed, but then the velocity effect is squared, so that's the next important thing. And then you have the density has is linear with density. But all these effects combined, you have a factor of 1,000 on the scale, but then you have a factor of the density ratio is almost a half, and then here you have a factor of 6/7, so maybe another 0.7 or 0.6. But you see, from 0.25 kilonewton meter, we got a huge number, 88 kilonewton meter. So this number is around 300 to 400 times larger than the prototype. Expected value is 300 to 400 times larger than the test model, which is a 1/10 scale model. So this is it about scaling and scaling up and scaling down. And this, in fact, by this problem, we conclude our chapter 5. We will post the take-home experiment on Tuesday, so we'll get a break in the next couple of days. And we will be moving next to talk about our last topic, which is flows in round pipes and non-round ducts. So thank you for listening, and I'll see you in the next lecture.